So this is the beginning of Chapter 2, which is titled Coherent Systems Analysis. The essence of this chapter is to determine the state of a system consisting of n components based on the states of the individual components. This chapter is particularly valuable for system designers who might be interested in determining ways to arrange the components in their system that they are about to design. The second part of this chapter is, given a system of components, what is the reliability of the system for a particular point in time. We begin with a number of definitions. The first definition, a system is an arrangement of n components. And when we draw block diagrams on the slides that follow this one, those block diagrams will have the components as a square box, usually with a number on it. Second definition, the binary assumption implies that both the components and the system can be either functioning or failed. So there are some systems where you can say the system is running at 60% capacity or 80% capacity. To simplify things, we don't allow that, and we assume that not only the system but also the individual components can either be functioning or failed. The third definition is the state of component I, which is denoted by x sub I, is 0 if component I has failed, 1 if component I is functioning. So our states that were defined up here by the binary assumption, functioning will be denoted by a 1, failed will be denoted by a 0. And those x sub i's, of course, are good for all n of the components that comprise the system. A couple notes at this point. First of all, the system state vector is x, which is the components x1, x2 through xn. Now, here and elsewhere in the book, when you see something set in boldface, that means that it is a vector. And that applies not only to the slides but also to the book. Another note is that by the multiplication rule, there are 2 to the n different values that the system state vector can assume. Since each one of these values can be either 0 or 1, you simply multiply 2 by itself n times and you get the different possible system state vectors. Finally, using combinations, n choose j of those 2 to the n different system state vectors correspond to exactly j functioning components for j equals 1 through n. So with those definitions in place, we move to something known as a structure function, and the structure function is the topic of this first section in Chapter 2. The structure function is denoted by phi of x, and the structure function maps the system state x to either 0 or 1, yielding the state of the system. So if you know all of the values in this system state vector x, might be 1, 0, 1, 1, 1, 0, 0, 1. If you know those, then the structure function will map those to the state of the system. So here's the definition. The structure function phi is 0 if the system has failed when the state vector is x, or it is 1 if the system is functioning when the state vector is x. So this same 0 and 1 is used as it was for the individual components. 0 corresponds to a failed system, 1 corresponds to a functioning system. Here is one particular type of system, and it occurs quite often in practice. It's called a series system, and here is its definition. A series system functions if and only if all of its components function. Another way of saying that is phi of x is equal to 1 when all of the components are functioning and 0 otherwise. So you have an operating system when all of the components are operating. There's something called a reliability block diagram, and down below here is that block diagram. You can think of it this way. If you put your finger right here on the far left, if you can trace your finger through all functioning components to the far right-hand side over here, then the system is operating. So here are three different ways of writing the structure function for a series system. The first way is to say that the system is up if all of the components are up, and the system is down if any one of the components is down. Now that's kind of a bulky way to write the definition of phi of x, so here is a more compact way. It is the minimum of all the x values. You need to think about that a little bit, but the only way for that minimum to return a 1 is for all of the individual x's to be 1s, which is to say every component has to be up. Finally, a third, even more compact way of writing the structure function for a series system is it's the product of the xi's. If all of those xi's are equal to 1, then when you take your product, you get a 1. But if one of them becomes a 0 and you multiply all the x sub i's together, you get 0, and that's exactly what you want. A couple examples of series systems. A Christmas tree lights, these are the old-fashioned kind, the more modern kind don't work this way, but old-fashioned Christmas tree lights used to be when a bulb would burn out, the whole string would go out. And then, of course, it was a lot of time to try to figure out which bulb burned out. You had to get a bulb that you knew worked and just work your way through the whole string of Christmas tree lights to figure out which one was the one that went out. So that's a series system. Human body has components which all have to work for the person to be alive. You have to have a circulatory system. You have to have a nervous system, digestive system, endocrine system, etc. Down at the bottom here it says a series system is the worst possible way to arrange n components. So this is one to avoid if at all possible. And I actually got a free car because of series systems. Let me show you how it worked. This was a 1953 Chevy. And what we have right here is that is a brake fluid reservoir. And on this 1953 Chevy, they had 4 brake lines in here. And one of those brake lines was ruptured right here. All of the brake fluid ran out. And then at that point, the brake pedal went to the floor, and the car was unable to stop. And the owner of the car was so disgusted by all the maintenance involved, he said, "You can have it for free." So I got a 1953 Chevy for nothing, fixed it for about 25 bucks, and owned it for a year and loved it. But this is a series system because you have 4 components, those 4 brake lines, and if any one of those goes out, the brake fluid drains. Now, there is about a 10-cent fix that they now do that makes a big difference. What they do is they put in a barrier right here between the two. And that is a very, very cheap way of improving the reliability, because if this brake line right here goes out, then only half of the brake fluid drains, and you still at least have 2 of the wheels with brakes. So you can redesign these systems sometimes very cheaply and improve their reliability. Well, a series system is the worst possible arrangement of n components. A parallel system is the best possible arrangement of n components. Here is its definition. A parallel system functions if and only if one or more of its components function. So phi of x assumes the value 0, which is to say the system is down when all of the components are down, and it is 0 otherwise. So what you have here is phi of x equals 0 if all of the components are down. Otherwise, phi of x equals 1 if you can find at least one component which is up. Here is a reliability block diagram off to the right of an n-component parallel system. You have components 1 through n labeled, so each one of these squares represents a component. Another way of writing the structure function is to write it as a maximum. The maximum of x1, x2 through xn will also work. So if you think about it, if you have all ones, if all of the components are up, then of course this will return a 1. Let's go to the opposite extreme. If all of the components are down, then all of these x's are 0, and the maximum of n zeros is 0, so the system is down as you would expect. Now let's try a mix. Some of them are 1s and some of them are 0s, which means some of these components have failed and others have not failed. When you take the maximum, you get a 1, and that's what you want for a parallel system. Finally, a third way of writing the structure function for a parallel system is it is 1 minus the product of 1 minus the xi's. And so if these xi's are 0s and 1s, I'll encourage you to go to those three cases, and those three cases are all of the xi's are equal to 1, all of the xi's are equal to 0, and some are 0 and some are 1. And as you plug into those three cases, you'll see that this formula gives you exactly what you hope it would. Okay, here are a couple examples. Kidneys are an example of a two-component parallel system. You can live with just one kidney, and some people actually donate a kidney to a sibling or somebody that's in need of a kidney. So that's one example of a two-component parallel system. And by the way, that is known a special type of parallel system in that it is an active standby system. That's quite different from a cold standby system. And when you take two pencils to an exam, you're not using both of those pencils at the same time. You're writing with one of them, and the other one is not subject to failure. And so that is known as a two-component cold standby parallel system. The brake fluid reservoir arrangement that you saw before had some parallel and series arrangements to it. Another example is I have usually 2 alarm clocks if I have to get up for a flight somewhere, for example. That's a parallel system. And even better if one goes off of the power grid and the other is a wind-up or the like. That's even better. Or battery operated is good too. I had heard that the Apollo missions would bring sometimes a spare computer, and I'm not sure if that was in an active or in a cold standby state. But that's another example. You can think of parallel systems as backups, and parallel systems are the way that design engineers try to improve reliability.